Okay, thank you. Thank you for joining our seminar today, and good morning, everybody. I'm Anna Deluca, and as Associate Professor at the University Mediterraneo of Reggio Calabria in Italy. My research field is about agricultural, food, and environmental economics, but in the last 15 years, my research group and we have specialized in methods and metrics for sustainability measurement of production processes, and in particular in the framework of life cycle thinking and tools life cycle based like life cycle assessment, life cycle costing, and social life cycle assessment to evaluate environmental, economic, and social sustainability dimensions. So we applied these approaches in several contexts within our research activities in several horizon projects funded by European Union, for example, to indicate the impact of agroecological practices in olive growing in Mediterranean areas with partners like Spain, Portugal, Greece, Italy, in Italy also other partners in Morocco and Tunisia, but the same methodologies also to assess the efficacy of different nature-based solutions in Denmark, Spain, Norway, and Turkey for another project, and with the aim to preserve the biodiversity in aquatic environment and to prevent aquatic pollution. Again, other applications are to analyze different production systems for textile industry or to evaluate logistic scenarios in large-scale retail to reduce or avoid food waste production and so to manage all impacts generated from it. So this is my general background, and today, as the title said, this webinar in the framework of StoRIES project will refer to sustainability aspects of energy storage solutions. This because in the last years I had the opportunity to contribute to write a volume, a Springer book as output of StoRIES project with an interdisciplinary view, including sustainability reflections. So my idea today is to provide you with an overview of the issues and problems, approaches, and methods to measure sustainability with the state-of-the-art of some applications of LCA methods in the energy storage sector with an holistic point of view and a particular focus on social aspects. So let's start. Let's start to giving you an overview of the contents of this seminar, and first we'll delve into some premises and into the main vulnerabilities of the battery sector by considering as crucial to understand the sustainability challenges this industry faces. Next, we'll explore whether we're looking at the acceptance or impact measurement. We'll break down the components of sustainability and discuss how we can measure them effectively. And finally, we'll transition to life cycle thinking, which is a tool internationally recognized for contributing to good practices in evaluation. We'll cover life cycle assessment, life cycle costing, and social life cycle assessment with a focus on some applications in energy storage solution. So this will highlights some results from a review of state of the art and set the stage for a discussion at the end of this seminar. So feel free to write in chat any questions. So, okay, let's go. And as a preamble, we must necessarily delve into a pressing issue in the battery industry, namely its focus on performance at the expense of the afterlife of batteries. This was highlighted by Nobel laureate Stanley Whittingham and is gaining attention in strategic documents like, for example, the World Economic Forum's battery vision, which argue that a circular battery value chain should not be just a vision. This transition should be pivotal not only for economic growth but also for advancing human rights, facilitating a just energy transition, and aligning with the United Nations Sustainable Development Goals. And this is also because the battery industry plays a crucial role in global electrification. If we imagine that it will be possible to provide electricity access to 600 million people and reduce so the gap of unelectrified households by 70% before 2030. So this represents the transformative power of batteries, key enablers for the energy transition and vital for achieving the European Green Deal zero pollution goals. And at the same time, let's keep in mind the potential of batteries to balance variable energy supply and demand, paving the way for smart energy systems. And as we are aware, batteries bring us remarkable energy and environmental advantages. However, it's crucial to recognize that their production has significant impacts. Key materials like cobalt, lithium, manganese, nickel, and graphite are essential, but their extraction raises serious concerns. The European Commission has taken an important step forward by implementing new battery regulations to enforce sustainability and ensure due diligence in mineral sourcing. It's a stride toward addressing the so-called decarbonization divide. That is a term used by experts to describe the risks emerging from the shift to a low carbon economy. And these risks, or also vulnerabilities in the energy storage sector, can be grouped into four main areas. First, environmental risks that are inevitable without stringent measures. Second, gender discrimination, that is a critical issue that needs addressing, always increasing. Third, child labor, which fortunately is not a global issue, but unfortunately in some regions of the world is a very plague. Even if from another point of view, it could be seen as the only way for families to make money. And so, how should it be viewed? Should it be seen as only a negative effect? Yes, but this is a paradox. This, for example, is one of the several theoretical problems and assumptions behind measuring social sustainability and positive or negative impact in social sustainability of production processes. Lastly, geopolitical and ethnic issues can have far-reaching consequences also. So, more specifically about these vulnerabilities from environmental and public health risk point of view, we could speak of it in terms of hidden cost of our devices, since when we talk about the materials used in many of our modern technologies, always there is a serious dark side linked to environmental public health risk. And these are not just minor concerns, they involve some fundamental issues for our planet and our well-being, of course. For example, in terms of resource depletion, this means that we are rapidly using up finite natural resources like copper, cobalt, nickel, thallium, and silver, so on, and even materials like lithium and aluminium are showing signs of strain, which is, of course, a bit worrying. Behind just running out, these materials pose also significant threats to living things. There's human toxicity, for example, meaning they can be directly harmful to people. Exposure can lead to a range of health problems, from respiratory issues to neurological damages. But also there is a problem of ecotoxicity, which means these substances are poisonous to the environment, impacting ecosystems, wildlife and plant life, and so on. Like a toxic spill in a river, it doesn't just affect the water, it harms everything that relies on that water. And pay attention, the problem is not confined to just one stage of a product life. Take raw material mining, for instance. This is where the story often begins, digging these elements out of the heart. And it is notoriously linked to several environmental pollution, including habitat destruction, water contamination, and air pollution. But the dangers don't stop there. There, serious health impacts can occur along the entire battery supply chain. And these include the processing of raw materials, manufacturing of components, assembly of the final product, transportation, and even the disposal or recycling of these items. Every step can expose workers, communities, and the environment to hazardous substances. Only to do some examples, the specialized scientific literature in this topic tell us that cobalt primarily harms the respiratory system, causing conditions like heart metal, lung disease, and asthma, and can be carcinogenic. Its meaning leads to severe land and water pollution, particularly in the Democratic Republic of Congo, for example. And also, nickel is a frequent cause of skin rashes, and when inhaled, can cause lung and nasal cancers and other respiratory issues. And its processing contaminates air, soil, and water, and it is toxic to aquatic life, but also other substances like copper, thallium, silver, lithium. Lithium used in batteries can be toxic in high doses, affecting the kidneys, thyroid, and nervous system. Furthermore, its extraction demands significant water resources in arid regions and causes land disturbance. Again, in terms of vulnerabilities, gender discrimination and the exclusion of women are important issues when we talk about diversity. For example, several studies on how well people accept new technologies like wearable biosensors sometimes look at gender differences. Namely, men and women accept these new health technologies differently. And another study found that men and women have different attitudes, perception, and values when it comes to battery electric vehicles. Understanding these differences could help in creating better policies to encourage more people to use battery electric vehicles. Finally, looking at the renewable energy industry, some organizations like the International Renewable Energy Agency and the International Labour Organization have pointed out that women make up only 32% of the total workforce in renewable energy. And this highlights a significant gender gap in this growing sector, as well as wage differences between male and female workers. Again, another risk is that in many countries where valuable resources are extracted, there are often no effective laws to prevent child labor and exploitation. For example, in Democratic Republic of Congo, for example, 23 of children, many orphans, work in cobalt mines, and as children face terrible conditions, including physical, psychological, and abuse, to earn enough to feed themselves and their families. This is happening despite some battery technologies using less cobalt. For example, the nickel manganese cobalt cathode battery still requires a lot of cobalt with tremendous consequences. Furthermore, regarding geopolitical or ethnic issues, the global demand for raw materials like cobalt and the need to process electronic waste extend behind environmental concerns, deeply linking with human rights and geographical inequalities. The control over these vital industries often leads to the suppression of ethnic groups, trapping certain communities in cycles of discrimination and inequalities. This dynamic also contributes to the displacement of people, leading to an increase in refugees and migratory workers who are forced from their homes in search of work, frequently under exploitative conditions within these same industries. These vulnerabilities are heavily concentrated in specific geographic areas. China, for instance, is a major focus. It's projected to see the most significant growth in energy sector employment by 2050. While this growth sounds positive, it highlights China's immense role in industries that often rely on this problematic material supply chain. In this meaning, another interesting thing, for example, regarding the geographical spread of the adoption of battery electric vehicles, that is very variable. Countries like USA, Japan, and the Netherlands have been more successful in getting people to switch to battery electric vehicles than others, such as South Korea or even China, despite China is central to raw material processing. So, achieving sustainability goals in the renewable energy sector and other clean energy ambitions is not just about new technology, it is heavily reliant on social factors. However, the shift to clean energy often gets stuck in a vicious cycle. Consumers hesitate to adopt newer, less established technologies, which keeps their prices high. In turn, investors are less keen to put money into products with low demand. So technologies like battery electric vehicles are still seen as innovative, leading people to perceive them as immature or risky. And so, summarizing the pressing sustainability challenges within the battery sector, we can say that first are related to the high greenhouse gas emission during production. And these emissions are a major contributor to climate change, and addressing them is crucial for our environmental goals. Next, there are significant social risks involved, where not just that, where we're not just talking we are not just talking about the environmental impact, but also the human aspect in terms of how communities and workers are affected by these practices. And finally, there's the uncertain viability of certain applications. As technology progresses, we must critically evaluate which applications are truly sustainable and beneficial. And to tackle these challenges, it is vital to conduct comprehensive assessment. This means rigorously evaluating advanced battery technologies through techno-economic simulation, cost-benefit analysis, and innovative business models also. Importantly, we cannot overlook the social and socio-economic impact. Our assessment must consider the welfare of workers and the implication for local community and society at large. The ultimate goal should be to strike a balance between fulfilling modern society's demands, respecting crucial social aspects, and ensuring environmental conservation. Now, one interesting thing to consider is that normally, while scientific literature is rich of studies that focus on environmental impacts of battery production or supply chain, the social aspect have been little investigated or limited to social acceptance, which is not really a social impact, but has to do with something else. So what is social acceptance? This deals with why we not always adopt new technologies, and especially green ones, and it is not always only a price question. Because adopting new technologies is not just about how well they work or how much they cost. Social factors play a huge role in whether people embrace them. And the so-called technology acceptance model here in this picture suggests that people are more likely to use a new technology if they believe it is useful or it helps them to something better. And also, if they believe that it is easy to use. And these two perceptions strongly influence their attitude toward using a technology and their intention to actually use it. More broadly, acceptance means that important groups like politicians, community leaders, and public passively or actively can approve of big energy technologies or related policies. It's about their willingness to support this initiative. And this framework breaks down social acceptance in renewable energy into three main areas: socio-political acceptance, community acceptance, and market acceptance. the socio-political acceptance. This is about how our governments make decisions and adopt energy policies. So if the law and the regulation are very supportive. The community acceptance deals with how local communities feel about new energy projects, concepts like the so-called NIMBY effect, not in my backyard, where people support a technology in general, but not if it's built near them. And this is an example of community acceptance. It's about understanding local concerns and also motivation. Market acceptance is about whether people actually buy and use the technologies in the market. When technologies are widely adopted in the market, it helps overcome barriers to even broader adoption. To do some example, the transportation sector is one of major polluter, responsible for about 11% of global greenhouse gas emissions, and electric vehicles, especially battery electric vehicles, are seen as crucial for cleaning up the sector, with over half of new cars expected to be electric by 2035. The battery is the heart of these vehicles, dictating their performance and also their cost. However, getting everyone to switch to electric vehicle faces several hurdles. For example, for the high cost, because battery electric vehicles are often more expensive upfront, or for the battery limitations, because concerns exist about battery range and the added weight of the battery pack. On the flip side, factors that encourage battery electric vehicles adoption can include the longer driving range, so the people that want to go further on a single charge, more charging stations, so to in terms of easy access to charging infrastructure, that is the key, and the lower prices, because as prices drop, more people will consider buying, of course, and eco-friendly attitude as a desire to protect the environment that could motivate some buyers. So while the environmental benefits of low carbon transport are more or less clear, the social side of electric vehicles adoption is also gaining significant attention from researchers. It is not just about the technologies, it's about people, perception, subjective belief, and so on. And but social acceptance is not an impact, as we have said. Social acceptance could be affected by reliable evidences on sustainability performance of one technology or another one. So we have inevitably to focus on sustainability assessment, but the question arises, which sustainability are we talking about? Sustainability is a multifaceted concept. It is not just about the environment, it also encompasses social and economic dimensions, and these prompt us to consider, are we looking at the environmental impact alone, or are we also considering the broader socioeconomic challenges and how we have to consider them? The same definitions and theoretical framework about sustainability concept not are always convergent. The most common vision of sustainability refers to the three pillars, the three well-known components of sustainability from Brundtland report from late 80s since today. Now, so the well-known our common future that suggests to meet the needs of the present without compromising the ability of future generations to meet their own needs. But also the triple bottom line from a business perspective, formulated by Elkington with the three P, profit, people, and planet, aimed to measure the financial, social, and environmental performance of the corporations over a period of time. Or again, the capital's approach of World Bank, suggesting that a country's wealth is the combination of various forms of capital, produced natural and human capitals that represents stock of wealth. Finally, the systemic approach of Frank Capra, renowned scientist, physicist, and systems theorist, argue that what is sustained in a sustainable community is not the economic growth or development, but the entire web of life on which our long-term survival depends. So, basically, what we call today the One Health approach or the New Green Deal for international governments. Therefore, the heart of the matter is the realization that our global problems are systemic problems, all interconnected and interdependent, and that the Sustainable Development Goals must also be seen as systematically interconnected. In this umbrella of concepts, actually, and especially for social aspects, we are trying to assess something that is not definite, neither consensual. So, how many pillars? Why just only 3? And how many indicators? The number of indicators for sustainability is vast and depends heavily on the specific context, scale, and goals of a sustainability assessment. There is not one universal set of indicators, but there are more or less comprehensive approaches. For example, the global framework is the United Nations Sustainable Development Goals, comprise 247 indicators ranging from environmental measures, namely CO2 emissions, renewable energy share, to social indicators like literacy rates, gender equality indices, and also economic indicators like gross domestic production per capita, employment rates. Furthermore, which importance we have to attribute to everyone. The true challenge and essence of sustainability lie in finding the balance and integration among these pillars. And which are the relationship among them? The relationship among the pillars are deeply interconnected and interdependent. There is an holistic interplay. Actions in one pillar invariably affect the others. For example, if we invest in renewable energy, so from economic and environmental sustainability point of view, we create jobs, so with consequence in social sustainability, and reduce pollution, so another consequences in environmental sustainability, and also leading to better health outcomes, again, for social sustainability, but also protecting biodiversity can support ecotourism, so economic impacts, and provide traditional medicines for communities, and this is another potential consequences, also both for economic but also for social aspects. Fair labor practices can lead to more productive workforces and a greater commitment to sustainable production methods. So this interconnected means that sustainable solutions often require integrated approaches that consider all 3 dimensions simultaneously, seeking win-win-win outcomes. And finally, another problem, what happens in the long run? The temporal dimension of sustainability, namely its intergenerational characteristics that often some assessment tools not consider at all or consider not adequately. So we face the problem of how to measure impacts in the most comprehensive, effective, robust, and reliable way. Back to the energy storage sector, since the world is quickly moving towards electric vehicles, for example, a huge increase in demand for batteries and metals is arising, but using and recycling these batteries takes a lot of resources, inputs, energy loads, and so on. To truly understand the impact, we need to look at every single step, from mining raw materials to recycling. And this is where life cycle thinking and life cycle based tools come in. Life cycle assessment, it's basically a tool to measure a product's potential environmental impacts during its entire existence. For batteries, many studies already use LCA to understand their environmental footprint, but also life cycle costing to calculate all the costs associated with the battery from its production and maintenance to its disposal. Life cycle costing provides a full view of whether a battery choice makes financial sense, considering both obvious costs, like purchase price, but also less obvious ones, like long-term economic effects. Life cycle costing helps decision makers understand the total financial state. While the social life cycle assessment, this is the newest and last developed of the three methods in the framework of life cycle, and social life cycle assessment focuses on the human and community impacts of battery production, highlighting issues like labor conditions, worker rights, and how communities are affected. It's crucial for understanding the full social consequences of making and using batteries, addressing a significant gap in sustainability studies. And social life cycle assessment could be essential for truly achieving sustainable product development. To get a complete picture, the life cycle thinking considers life cycle sustainability assessment, which should be able to combine all three dimensions and all results delivered from the single methodologies. So the standardization of these assessment methods is crucial for making results comparable and reliable. In this slide, a simplified overview of the main international organization for standardization norms, ISO norms, that life cycle methods are based on. So the core ISO standards for environmental life cycle assessment is the 14040 ISO and the 14044. These two standards work together, setting the broad principle and providing the specific steps and requirements. They ensure that life cycle assessments are conducted in a consistent and transparent way worldwide. Other related ISO standards specifically focus on calculating a product's carbon footprint or water footprint based on these life cycle assessment principles. instead, for life cycle costing, unlike life cycle assessment, there is not one single ISO, but life cycle costing principle and methodologies are often integrated into other standards, particularly in specific sectors. So the principle of comprehensive cost assessment over a life cycle are widely recognized and applied in various industry-specific contexts and directives, like those from the European Commission for Public Procurement. Anyway, one of the most important references is the 15,600 and 86.5 ISO that provides guidelines for life cycle costing, specifically within the construction sector, looking at the cost of building and other constructed assets over their entire lifespan. So standardization of social life cycle assessment is more recent and still developing compared to life cycle assessment. However, a specific ISO has now been published, the 14,075 ISO, that this is the key standard and provides a structured framework, principle, and guidelines for assessing the social and the socioeconomic impacts of products during their whole life cycle. This ISO helps define how to identify social issues like labor condition, human rights, community impacts, collect relevant data, and interpret results to understand the social footprint. So, for example, with a life cycle analysis and a life cycle assessment in particular in this slide, we can cover a battery's entire journey to answer these questions. Where do the metals come from and how are they extracted? How are battery components made? What's the impact while the battery is in use? In an electric vehicle, for example, what happens when the battery is no longer useful? Applying environmental life cycle assessment early, even for new technologies, helps identify hotspots of environmental harm and avoid unexpected problems before product hit the market. So when we want to understand the environmental impact of a battery, we start with a crucial first step, as suggested by ISO norm, defining the goal and the scope of our study, ensuring the study is clear, consistent, and well defined from the beginning. In this initial phase, we have to set out some specific items. So what we want to achieve, what are the objectives of our study, how are we comparing different battery types, looking at how to make batteries more efficient, or examining the impact of specific production stage. We have to decide this. The unit is an also very important item. So the unit we are measuring, this is called the functional unit. For batteries, it's typically 1 kilowatt-hour of energy capacity, like measuring how much energy it can store, or 1 vehicle kilometer, if we are looking at the battery's impact in a car over a certain distance. The choice depends on what we are trying to compare or evaluate. So the boundaries of our study is another important item, and this defines what is included and what is left out. The main options are cradle to gate, from raw material extraction to the factory gate before it's used, or cradle to grave, from raw material extraction to disposal, or cradle to cradle, from raw material extraction throughout use, and then back into a new product throughout recycling. Choosing the right boundary helps ensure the correct evaluation between comparable scenarios. How we will do it? This includes selecting the specific methods, how we will allocate impact, especially if a process creates multiple products, and which impact categories like climate change, water pollution, and so on, we will measure. The other fundamental steps of life cycle assessment, as suggested by ISO norms, are the so-called life cycle inventory and life cycle impact assessment and interpretation of results. So to realize the life cycle inventory, we have to say that conducting an LCA of a given product requires data that tracks the materials and energy input and output associated with the production, the use, and the end-of-life management processes for that product. This data consists of both direct input and outputs from processes directly involving the product itself, as well as inputs and outputs associated with the systems that provide those inputs. And these data sets are developed from multiple data sources, including but not limited to material supplier data, manufacturer data, trade data, academic literature, and regional government databases. Certain battery technologies have relatively mature life cycle assessment data sets and subsequently a robust literature of life cycle assessment that characterize them. So the life cycle inventory is essentially the data collection phase, where we gather detailed information on all the inputs and outputs at every stage of the battery's life cycle. This data collection is extremely important because it forms the backbone of the entire life cycle assessment study. It's often the most demanding and time-consuming part of the process, requiring detailed, comprehensive and reliable information for each step in manufacturing and usage. The accuracy of our final assessment heavily relies on the quality and completeness of this inventory data. There are two main types of data we can collect. The foreground data, but also the so-called primary data. This is specific direct information obtained straight from the source, like a battery manufacturer. For instance, it would include exact figures on the energy used, the materials consumed, and the emissions produced within their specific factor. This kind of data is incredibly valuable because it's precise and unique to the product being studied. However, it's often highly confidential and very challenging to acquire because companies are protective and of their operational details, so it could be a problem. The background data, this other type of data, also named the secondary data, is usually broader and comes from existing sources of estimations. It is often found in large LCA software database like EcoInvent, European Reference Lifecycle Database, and other related to the specific sector. This database contains pre-calculated environmental profiles for common industrial processes, raw material production, and energy generation. We also can use data from published scientific studies as background information. Background data helps fill in the gap for processes that are not directly managed by the battery manufacturer. For example, the electricity grid mix or the production of basic chemicals. So the other phase in life cycle assessment method is the life cycle impact assessment, and this phase quantifies potential environmental effect based on data from the life cycle inventory stage. And in terms of impact categories, so variability in results often stems from differing methodologies, database, and battery chemistries. CIMAPRO and OpenLCA are commonly used software tools for this assessment, and life cycle impact assessment primarily uses two impact categories: midpoint impact categories, so parameters in the cause effect chain before the final impact, and endpoint impact categories, so the aggregates of midpoint categories representing the final environmental impact. The recipe method is one of the most commonly used for characterization life cycle impact assessment, and use 18 midpoint indicators that are specific environmental issues such as global warming, potential or acidification. Think of them as points along the cause-effect chain before a final impact is fully realized. Recipe also use 3 endpoint indicators, which are much easier to understand but come with higher certainty. These endpoints measure the ultimate damage caused by stressor at the very end of the cause-effect chain, and there are human health, ecosystem health, and natural resources, for example. So moving to the life cycle costing, it focuses on flows in connection with the production and consumption of goods and services, and it is an economic approach that sums up the total cost of a product, process, or activity discounted over its lifetime, and it is associated with all costs occurring from purchase to disposal, and can include the cost of externalities like environmental cost. The idea is that the purchase price often does not reflect the full cost caused by a product over its whole life cycle, and thus it is not a sufficient indication. So a robust life cycle framework will be able to link life cycle assessment studies to the monetary cost systems used by business decision makers. There are 3 main types of life cycle costing: conventional, environmental, and societal. Societal life cycle costing is very similar to life cycle assessment, also for LCC goal and scope, system boundaries. The object of the study, allocation, impact assessment, and other aspects need to be defined and aligned with the decision taken for the life cycle assessment in order to obtain an overall consistent analysis. So in the case of battery life cycle cost, for example, we can evaluate the total cost of a battery system over its entire lifespan. This includes cost for production, installation, maintenance, and disposal. And basically, LCC is the sum of some economic indicators like capital expenditures, so initial cost like purchasing, installing the battery, covering design, engineering, procurement, and construction, but also operating expenditure, ongoing cost such as energy use, maintenance, and repairs throughout the battery's operational life, and finally also economic indicator like end-of-life expenditures, so cost associated with disposing of the battery after its useful life, including transportation, disposal, and environmental remediation. So by looking at the complete life cycle cost, organization can make smarter decisions about product selection, potentially reducing overall cost and boosting corporate sustainability. For example, a battery with a low initial price might end up costing more over its lifetime due to high operating and or disposal expenses. So life cycle costing studies often compare different battery chemistries like lead acid versus lithium-ion for stationary energy storage. Differences in performance, lifespan, safety, and recycling cost significantly impact the total cost of ownership. So finally, life cycle costing can be assessed for various perspectives. Customer, manufacturer, or society as a whole, and scopes including conventional, environmental, and societal LCC. Now, when transitioning to social life cycle assessment, a significant number of considerations arise, primarily stemming from the very nature of the social phenomena we aim to analyze. And this is inherent complexity is deeply tied to the elusive character of social sustainability itself. The challenge lies in effectively interpreting and framing this multifaceted social phenomena. Unlike environmental impacts, which can often be quantified with relative precision, social impacts are frequently subjective, context-dependent, and influenced by different cultural values and perspectives, so on. This inherent difficulty in defining methodologies, in defining and measuring the social aspect has over time led to a wide array of distinct approaches and methodologies for analyzing social impact within the social life cycle framework. And this rich but yet fragmented landscape reflects the ongoing effort to capture the nuanced realities of how products, service, and organization affect human well-being across the entire life cycle. Therefore, we still have a social life cycle assessment that is not well defined despite the ISO standard, and that is still subject to many different methodological interpretations. For example, the fact that social life cycle assessment has been conceived in the technical and economic milieu of environmental life cycle assessment, and that most of its practitioners and scholars are usually engineers, chemists, or physicians, led to framing and shaping the assessment methodology of social impacts in the same way it has been done for environmental impacts in environmental life cycle assessment. However, the social pillar is still seen as weaker regarding its level of methodological advancement of assessment methods and conceptual recognition. Social life cycle assessment faces barriers in terms of quantitative data availability, leading to difficulties in adopting similar system boundaries to life cycle assessment, and show great immaturity on methodological issues in impact assessment, result interpretation, and user friendliness compared to life cycle costing and environmental life cycle assessment. So the we can say that natural science, like mathematics, physics, chemistry, have always been consensually dominated by so-called positivism-oriented philosophies, mainly characterized by quantitative methodologies devoted to the explanation and prediction of phenomena. To the application of experimental approaches and empirical validation according to a deductive principle. So for a long time, the disciplines of natural science have been considered the only ones that deserve the dimension of science, and their typical methods were considered the only scientific methods. Instead, the management science, from an academic point of view, are the youngest of the social sciences that only recently have gained the mention of sciences. It is a very complex disciplinary field. Moreover, management science being a relatively new science and multiple paradigms coexist, many theories are applied and different techniques are developed. And so finally also sociology, that is the analysis of the structure of the social relationships as constituted by social interaction, but no definition is entirely satisfactory because of the diversity of perspective which is characteristic of the modern discipline of sociology. So when we talk about social life cycle assessment, we have to explore the fascinating world of paradigms in scientific research that influence how we observe social phenomena. And we have to consider three interrelated elements: ontology, that is about the nature of reality, and epistemology, that is the questioning how we know what we know, and it's about the source of our knowledge and its justification, and this element challenges us to consider what can be known and who holds that knowledge. And finally, methodologies that, as Corbetta suggests, this involves moving from theory to empirical research, so transforming hypotheses into concrete concept and variables, and it is the practical pathway that guides our research journey. So these elements from the cornerstone of what Kuhn describes as paradigms universally recognized scientific achievement that provide models for problem solving within a community. And as Ruben Lincoln note, paradigms serve as a worldview guiding investigators in their research pursuits. So while positivism-oriented philosophies have dominated the scientific research in the field of the so-called hard science. In the development of sociological theories, it is difficult to recognize a dominant paradigm, and more worldview have been held simultaneously. That is why sociology is considered a multi-paradigmatic science. So as the lines between paradigms are often very fine, and this table shows two main orientations, positive and interpretivism, that can be considered the umbrella to which almost all of them tend. And we can see the two approaches using the Taylor and Medina analogy of a fisherman that beautifully illustrates the core difference between positivist and interpretivist research approaches. In the case of positivist, so the fisherman as a pure observer, the fisherman describing the social characteristics of a fish population by simply observing how they swim. The positive researchers aims to identify objective, measurable patterns, a causal relationship in social phenomena. They seek to quantify, categorize, and generalize findings, much like counting fish, measuring their speed, or mapping their observed movements. The focus is on what can be directly observed and empirically verified, with the goal of developing universal laws or theories. In contrast, the interpretivist approach is more complex and comprehensive, considering other elements and aspects interrelated to the behavior of the fish. And this would involve not just observing the swimming, but understanding why they swim that way. And are they responding to water temperature, the presence of predators, mating rituals, food availability, or even the type of currents? The interpretivist would delve into the context, meanings, motivation, and subjective experiences that shape the fish behavior, seeking to understand the deeper layers of meaning and the intricate web of relationships that influence their actions within their natural habitat. So they aim for rich, in-depth understanding rather than broad generalization. So this methodological diversity reflects also the different approaches that we found in social life cycle assessment studies due to the specific characteristics of social sciences, which are multi-paradigmatic, and many world of view can be held. Indeed, many scientific methods are available for the assessment of social phenomena, such as quantitative, qualitative, and mixed methods. Therefore, up to now, both interpretivist and post-positivist epistemological positions have been applied in the social life cycle assessment scientific literature, and most of the studies published have been evaluating in a qualitative or normative way a wide range of impact categories, mostly linked to companies' behavior. So, for example, for child labor, corruption, fair wage, safety, rather than to the life cycle functioning of the production processes. Few studies can be found in literature quantifying the cause-effect relationships between life cycle functioning and areas of protections in an objective and generalizable way. So further efforts should be made on standardization possibilities and the alignment of other life cycle methodologies, and testing of methods is necessary to overcome present obstacles and increase the applicability and interpretability result. So actually, the main approaches most commonly adopted refer to the isosocial LCA norms and the updated guidelines of UNEP-SETAC and the methodological sheets for subcategories in social life cycle assessment, which provide a methodological overview for practitioners about possible evaluation procedures. According to them, there are two main impact assessment approaches, and each of them respond to different practical research aims. So the reference scale approach, the type 1, and the impact pathway approaches, the so-called type 2. So the reference scale evaluates a company's or organization's social performance or risk by comparing their actions to a set standard like regulation or norms. And this assessment relies on current data, stakeholder opinions, and is generally a short-term snapshot rather than an accounting of long-term impacts. And as a result, the characterization process is largely based on interpretation. The reference scale refers to performance reference points, so results are expressed using performance reference points, which are threshold targets or objectives that set different levels of social performance or social risk, and these help estimate the magnitude of potential social impact, but they are highly dependent on the specific context, international standards, local laws, or industry best practices, making them not easily generalizable. Furthermore, there are some limits and constraints, for example, in terms of data, because reference scale approach often involves a variety of qualitative approaches for data collection interpretation, and also the use of functional unit for scaling inventory input is frequently optional, and the characterization step often involves explicit or implicit value judgment on the collected data. So there are also disregard for core lifecycle assessment elements. Studies in this typology sometimes overlook typical lifecycle study items like system boundaries, time frames, cutoff criteria, and evaluation of individual lifecycle phases. Furthermore, they provide a qualitative assessment of social performance, relying on value judgment and varying relative weights for result characterization. And also the characterization methods typically involve comparison to norms, best practice, socioeconomic context, stakeholder judgment on compliance, expert evaluation, or comparison of alternatives. So in qualitative terms, always. In a sense, the type 1 of social lifecycle assessment offers a qualitative snapshot of social performance, but its context dependent nature and reliance on interpretation present methodological challenges. On the other hand, the reference scale approach has specialized databases like PSILCA, Product Social Impact Lifecycle Assessment, and Social Hotspot database that are available and provide social impact information for products across their life cycles, covers nearly 15,000 industry sectors and commodities, and includes, for example, PSILCA, 69 qualitative and quantitative indicators, or social hotspot database that uses multi-regional economic input-output data and links local and global supply chains to various social metrics by sector and country. So for the type 2, the impact pathway approach of social lifecycle assessment, this aims to predict the consequences of a product system by evaluating actual or potential social impact by establishing causal or correlation regression based relationships, known as impact pathways, between the product or services life cycle and social impact, whether short-term or long-term. The characterization process in type 2 social life cycle assessment involves an analytical and quantifiable identification of these consequences. So some examples are the so-called Preston pathway proposed by Feshem et al. That assesses social impact by linking increased economic activity to income growth, which in turn leads to improved public health, for example, or Wilking pathways introduced by Bokum et al. That examine how changes in income distribution within a population triggered by a significant life cycle event can alter the infant mortality rate, for example, and so also furthermore, the so-called psychosocial risk factor impact pathway proposed by Jofrida et al. In my research group and that quantify the risk of psychosocial impacts on various stakeholders during a product's life cycle, and it considers the duration of exposure to specific living and working conditions that could cause health problems like aspect of work planning and management that can potentially lead to physical or psychological harm. And psychosocial risks are measured using odds ratio, that is a statistical tool that indicates the strength of the association between two variables. And normally data source for psychosocial risk factor pathways comes from existing epidemiological scientific studies that analyze a relationship between specific living or working condition and health issues. So now, after this overview about the life cycle methods for sustainability assessment, I would like to report you some findings of an interesting review of last year by Paul et al. That provides a comprehensive review of the sustainability dimensions in the case of lithium-based batteries, focusing on their environmental, economic, and social impact throughout life cycle methodologies, with the aim to bring together and integrate the three pillars of the sustainability tools in coherence. And throughout this work, basically a critical overview of previous life cycle studies on lithium-based batteries is presented. So key point included in this review are related to the types and applications. So lithium-based batteries, Li-ion, Li-metal, Li-air, Li-polymer, and Li-sulfur that are widely used in electric vehicles, grid scale, energy storage, portable electronics, and medical devices. So Li-ion batteries are the most popular due to their longer life cycle. So the environmental life cycle assessment can evaluate the environmental impacts of battery production, use, and disposal. And key contributors to environmental impacts include energy consumption during manufacturing, cathode production, and electricity usage. And other findings reveals that emerging battery technologies like lithium sulfur and lithium air show promising environmental benefits over conventional Li-ion batteries. So the most important application for assessing the impact of the battery product over its life cycle lies in dissecting the contributions of individual life cycle stages. As already said, moreover, battery production includes raw material extraction, mainly in the form of mining ores, production of battery components, battery modules, and battery packs assembled with a battery management system, followed by the transportation of the products, their usage, and of life or recycling. So in terms of results for goal and scope step of LCA, in the reviewed articles given, most of the functional units considered were either 1 kilowatt hour of the nominal energy capacity or 1 vehicle kilometer. So the determination of the functional unit is guided by the specific objective of the study, including the comparative evaluation of environmental performance across different vehicles or different battery chemistries. Investing in the battery efficiency or examining different phases of battery production. The three system boundaries that were frequently used in this type of assessment represent to represent the entire life cycle of an electric vehicle, where cradle to gate, cradle to grave, and cradle to cradle. So regarding the life cycle inventory phases, reviewed studies on batteries show a significant reliance on secondary data, and often from existing databases or software. Only 45 of studies combine primary data directly from labs or industry with secondary data. And these primary data typically include details on battery production materials, energy used during production and use, and waste recovered materials. The majority of studies, however, depend entirely on secondary data. Furthermore, transparency is a major hurdle. Only 35 of reviewed studies have open access inventory data, and 38 completely lack open inventory data. So the rest provide only partial data, and this lack of transparencies make difficult to ensure accurate comparisons of environmental impacts and can lead to unreliable conclusions. Open and consistent data is crucial for improving the reliability and validity on battery life cycle methodologies. So for life cycle impact assessment, this phase aims to quantitatively and comparatively evaluate potential environmental impact, and the recipe method has been used 50 out of the 31 case studies as the most common characterization tool, and as impact categories in the reviewed works, it was observed that all studies included in the analysis integrated the calculation of global warming potential, and also other impact categories were resource depletion, acidification, humotoxicity, and eutrophication. So battery production processes, particularly coating and drying, formation and drying rooms, are energy intensive, consuming over 76 of total energy and contributing to 74 of greenhouse gas emissions. The cathode and the electricity used for material transformation and battery assembly are also major global warming potential drivers, accounting for 40.5% and 70% of the overall impact, respectively. In summary, the studies emphasized the importance of considering global warming potential together other environmental impact category in assessing battery production and use. The results also showed that emerging batteries like Li-sulfur, lithium, manganese metals, and Li-oxide showed promising environmental benefits over current lithium batteries. In terms of interpretation of result, this final stage of LCAs involve interpreting results to pinpoint environmental hotspot, and in terms of energy consumption factor, for example, battery cell manufacturing, particularly energy-intensive processes like cathode paste production, cell container fabrication, vacuum drying, and coating are the main environmental impact drivers. And furthermore, energy consumption during the battery's use phase is critical, with primary electricity usage data significantly affecting the overall environmental impact assessment. So in terms of novel material factor, the latest batteries using nickel, manganese, cobalt cathode or anode made of silicon alloy and sapphire electrolyte are more eco-friendly than older batteries that use graphite, and the nickel, manganese, cobalt, lithium battery, which uses an nickel manganese cobalt cathode and a lithium metal anode is currently the greenest option for its storage capacity, and it also lasts as long as or even longer than batteries with graphite anodes. Because of its high capacity, lightweight, and environmental benefits, the lithium metal anode is expected to be a key material in future electric vehicle batteries. So, when it comes to environmental performance, lithium iron phosphate batteries generally outperform nickel manganese cobalt batteries. This is mainly because nickel manganese cobalt batteries use rare metals like nickel, cobalt in their cathodes, which have a higher environmental impact during production compared to the materials in the lithium iron phosphate batteries. Lithium sulfur batteries also are emerging as a sustainable energy storage solution, primarily because they don't use toxic metals like nickel, cobalt, and manganese found in traditional ion batteries. The inclusion of sulfur in the cathode significantly enhances their environmental profile. So these batteries show great promise for electric vehicles, offering higher specific energies than lithium batteries and reducing the need for raw materials. In fact, Li-sulfur batteries can lead to a reduction of up to 31% in greenhouse gas emissions compared to lithium batteries. However, it's important to note that the production phase of Li-sulfur batteries, encompassing material extraction and component manufacturing, still contribute significantly to impact categories such as abiotic resource depletion and natural resource scarcity. So battery recycling factor is another item for interpretation of the result, because recycling batteries can significantly cut down their environmental impact. By using recycled materials instead of new ones, we can reduce overall impacts by 25% to 46%. Specifically, recycling cobalt, nickel, and copper in batteries dramatically lowers their environmental footprint, because it means we don't have to mine as much new raw materials, of course. So, life cycle costing in these findings from the review is about the examination of cost at different levels, from individual battery cells to full electric vehicles. They usually focus on either the cost to produce the battery or the user's operating cost for an electric car. These costs are typically measured in a country's currency per kilowatt hour of battery capacity or at the specific system level, and most of the studies cover the entire battery lifespan from cradle to grave, so from production to disposal, but also from cradle to usage, from production to active use, and some are also to cradle to gate, so from production up to the factory gate. And the quality of life cycle studies depends heavily on their data, and the researchers mainly get the information from secondary sources like public or restricted databases, other research papers, market data, simulations, or expert opinions. So global organizations such as the World Bank, Eurostat, and the United Nations Trade Database are common sources of this data. And in life cycle costing studies, the impact category is always about cost, but from different angles. Typically, studies focus on conventional LCC, which include both variable and fixed cost. However, they also evaluate environmental cost, often expressed as the monetary value of greenhouse gas emissions, usually in Euroton CO2 equivalent. In terms of interpretation results, the findings from the review suggest that battery electric vehicles and diesel-powered internal combustion engine vehicles are generally the most affordable choices for consumers, and their total life cycle cost can be around 5% lower than petrol-powered engine vehicles and 50% lower than hybrid electric vehicles. However, it's important to note that market prices alone are not always enough to promote sustainable resource use. A key reason for the higher initial cost of battery electric vehicles compared to traditional combustion engine vehicles is the high cost of battery production, of course. For lithium-ion batteries to be widely adopted, their price must decrease and their cycle stability, how long they last, must be high. Achieving economies of scale in manufacturing can effectively lower battery prices by fully utilizing production plant resources. So the overall cost of electricity storage in batteries is largely determined by the battery system cost itself. However, greenhouse gas emissions for charging, especially due to round-trip inefficiencies, energy lost during charging and discharging, for example, significantly add to a battery's life cycle emissions. To reduce these emissions, increasing the proportions of renewable energy in the electricity grid is crucial, as it also indirectly lowers emissions from the electricity used during battery production. Finally, a battery's lifespan, typically estimated at 80 years, 8 years, is another factor that influence its price. And results show that the review show that it can optimize battery cost by adding thermal energy storage to a large battery rather than just partially replacing the battery itself. Economic factors like fuel cost, its price increase, and the discount rate evenly influence the overall cost. So, combining solar, for example, solar panels with a diesel generator can cut total cost by 9–10%, and adding batteries reduce them even more by 40–17%. While combining batteries with thermal energy storage offers significant fuel savings compared to batteries alone, it does increase initial investment also. Lastly, cars using batteries, lithium batteries typically consume more energy and produce more emissions during use than those with lithium, nickel, manganese, cobalt batteries, negatively impacting their overall greenhouse gas footprint. So, in conclusion, electric vehicles with lithium iron phosphate batteries are as good as, or even better than those with lithium nickel manganese batteries in terms of environmental impact. And this is because lithium iron phosphate batteries materials create fewer emissions, and making the vehicle itself is the biggest factor for these environmental metrics. On the other hand, lithium, nickel, manganese, cobalt batteries are more cost-effective, which helps both consumers and society by lowering external cost. So, obviously, to get the best economic impact on the environment, we need to reduce the cost of batteries and solar powers, solar power also. In terms of results from social life cycle assessment, while environmental and economic aspects for sustainability are frequently studied, in the social pillar remains the least addressed in the context of lithium-based batteries and of the findings from this review. Unfortunately, because it could usefully helps to inform all stakeholders, from retailers to consumer, about the social impact of the lithium batteries they interact with. So this awareness aims to prevent negative social impacts from simply shifting between different stages of a battery's life cycle or from one social issue to another. So social life cycle assessment for lithium-based batteries is crucial for several reasons. So it aims to monitor manufacturer and raise awareness among retailers, the public and consumers about the social impact of this product. Therefore, conducting a social life cycle assessment for lead-based batteries is key to creating genuinely sustainable lead battery products and manufacturing process. In terms of goal and scope, there is reviewed studies on lithium batteries. The social LCA approach is the type 1, namely the UNEP-SETAC guidelines, and helps identify social hotspots within the supply chain. One challenge is that users and stakeholders are often underrepresented in battery-related social life cycle studies when identifying and prioritizing impact subcategories, and the specific indicators used vary, but common examples include working condition, community and infrastructure, and legal system, or a combination of general and specific indicators for each impact category. Interpretation, the interpretation of the results is related to the socio-economic impacts on workers, the local community, and the society that differ in the type of meaning, techniques, and socio-economic status of countries, and thus the social life cycle assessment needs to be tailored to the local context necessarily. So results showed also that social repercussions of batteries of electric vehicle supply chain are very poorly considered or are limited to social acceptance, and difficulty due there are some difficulty due to different social life cycle assessment methodologies that is not yet standardized, for the complexity of the indicators choice and the obstacles to obtain data from the specific production sector, and for all life cycle phases. Especially it is true for raw materials extraction and processing, which seems to be the riskiest stage in terms of impact, but also the production of intermediates, the production of battery cells, the assembly of the battery pack as a final product, and the disposal of recycles. Finally, on the other hand, from an exclusive social point of view, the inclusion in the same investigation of impact evaluations of different type of stakeholders remain a very challenging issue, and most analyses are always the workers group, with the recurring impact category on work conditions, health and safety, freedom of collective bargaining, fair wages, and child labor. And there are always necessity of more research to clearly define the possible social impacts of batteries, especially objective analysis that can clearly quantify the impact deriving from the life cycle phases, and that allow comparison among different scenarios, which can be highly variegated and differentiated. Thank you for your attention, and these are the main conclusion of our seminar. With this, that's all, and thank you for your attention.